Okay, good morning, everyone. Thank you so much for joining us today. My name is Victoria, and I'm a Senior Business Development Coordinator at 2H Offshore. We started this webinar series last year in April during COVID lockdown and held a live webinar every 2 weeks in 2020. Going forward, we'll be hosting the events monthly, so we hope you will continue to join us and find the information useful. Today, our webinar is entitled Key Challenges of Managed Pressure Drilling Riser Stack Integration. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. So with that, I'm very happy to introduce our speaker today, Sean White. Sean is a principal engineer at 2H Offshore and has over 16 years of experience in R&D, systems engineering, equipment delivery management, and installation operations. He is based in 2H's Houston office, where he leads multiple engineering projects, as well as technology development programs such as MPD riser integration, MPD system integration testing, and MPD equipment qualification testing. Sean holds a Bachelor of Science degree in Aerospace Engineering from Embry-Riddle Aeronautical University. So with that, I'm going to pass things over to Sean to get us started today.
Yes, thank you, Victoria, for that warm introduction there. I'm excited to be here today to pass on some of the key findings that we've had in MPD riser stack integration over the last few years. And with that, we'll get going with the presentation here. We have about 30 minutes today, so MPD is quite a vast topic, and MPD, we selected this topic today to give everybody a general understanding of what some of the key system integration activities you want to consider when looking at integrating a managed pressure integrated riser joint, or IRJ, into a marine drilling riser system for an offshore drill ship or semi-submersible MODU. The two key areas we want to focus today on the webinar are related to the two interfaces that are most commonly assessed at first when putting an IRJ into a drill rig, and that's going to be the interface between the marine drilling riser itself and the IRJ. And what we're going to go over there are what specifications and design and fabrications you're going to have when considering in development, design, and fabrication of riser crossover adapters. The second half of the webinar is going to focus on the vessel to MPD IRJ interfaces, and by those two key areas we'll be focusing in there are related to placement of MPD flexible hoses in the moon pool, and how those hose operating performance is affected by the placement of the hoses in the moon pool. And we'll be also reviewing riser handling equipment that'll allow you to focus on key areas you need to look into very early on in the project to make sure your IRJ equipment can be safely lifted, installed, and serviced effectively while you're on critical path doing a drilling riser installation or retrieval. Your typical MPD IRJ configuration that you're going to see in most deepwater drilling activities today requires a below tension ring managed pressure integrated riser joint placed just below the telescopic joint. The joint's often placed just below the telescopic joint because what it does is it minimizes the length of the flexible jumpers that you have to have hung off on the side of the drill rig's moon pool and hung below the hull all the way down to the IRJ. The reason we highlight this here is for most drill ships and semi-subs, your flexible jumpers for your choke and kill lines, your mud booster line, and your hydraulic lines don't typically extend that far below the hull. But when you start looking at MPD IRJs, the hoses can extend to quite long lengths. We've seen installations where you may have a keel joint, you may have a termination joint, or even a pup joint placed below the telescopic joint and the IRJ. The keel joint and the termination joint may be based on that rig-specific riser stack-up, but oftentimes drilling contractors do look at putting a pup joint between the telescopic joint and the IRJ itself, and that can be put in place just to get your space out proper to have enough distance when you have the pup hung off in the spider that the MPD IRJ could be an acceptable working height for any work platforms that you may have in the moon pool. What these additional joints do is it's going to increase the length of your flexible jumpers that extend below the hull. And we've seen some instances where jumpers have ranged from 220 feet all the way down to 330 feet below the hull. And that'll be something key that we focus on when we get to the second half of the presentation at looking at vessel to IRJ interfaces. So, excuse me here, sorry, I bumped that a little too fast. The first topic we wanted to talk about was the marine riser interface to the MPD IRJ. And one of the most common questions we get here are why are marine riser crossover adapters required to put an MPD IRJ into the marine riser system? They aren't always required, but typically the reason why you'll need them is many MPD service providers have a standard set of flanges or interfaces that's at the very top and the lower half of their integrated riser joint. And oftentimes those riser flanges could be API flanges, they could be custom marine drilling riser flanges specific to that MPD service provider's OEM kit. And what we need to do is to be able to have a way to adapt from the rig's existing marine riser flange and cross over and adapt to the MPD riser specific flange. So the crossover adapters are just the means to facilitate getting the connection so you can insert the IRJ seamlessly into the riser string and while still allowing the rig's choke and kill lines, mud boost line, and hydraulic auxiliary lines to have a continuous conduit through the MPD IRJ. The key crossover adapter design considerations you have to play is very early on, you're going to want to have a stakeholder management plan. And what we mean by that is you have numerous players involved when you start looking at integrating an MPD riser system into your asset. So you're going to have typically the operator, the drilling contractor, you'll have riser OEMs, you'll have your MPD service provider, and you may have third-party design representatives or even third-party certification authorities like ABS and DNV. Making sure that all those parties come together and understand the roles and responsibilities and requirements and getting information so you can adequately design your crossover adapter from the drilling contractor and the riser OEM is really beneficial in helping making sure you have a smooth execution when you're designing your crossovers. Perhaps one of the key challenges that you want to consider early on in your project is what type of riser system do you have? Typically today there are two riser systems classifications out there. Those would be load sharing versus non-load sharing. And on the next slide we'll define what that means. But that distinction can drive if your crossover adapter design could be fairly complex or fairly simple. One of the aspects that crossover designs have to consider is managing the geometry changes that come across with different orientations of your auxiliary lines. The lines may have different clocking positions between the MPD service provider IRJ and the existing marine riser. The auxiliary lines could have different sizes, and what I mean by that is one rig may have a 4.5-inch choke and kill line ID, another rig may have a 4-inch choke and kill line ID. And the MPD service provider kit may have auxiliary line IDs for the choke and kill lines that goes all the way down to 3 inches. So you have to deal with the size of the aux lines, and then you may have different offsets from riser center line. So looking at the aspect of load sharing versus non-load sharing, this can really start to impact what the overall load rating of your MPD IRJ is. There are two systems out there today, and a load sharing system, which is one of the more common types of riser systems out in the market, is if you look at the load path between the marine drilling riser all the way down to the wellhead, typically with a load sharing riser, you're going to take 70% of the tension load through the main tube, and you're going to split 30% of the tension load to the aux lines. That's just trying to take benefit of the fact that the choke and kill lines or the aux lines are fairly rigid and strong structures, so you can try to balance out the load between the main tube and the aux lines, which helps minimize the overall weight of the riser system. You'll get into, also there are non-load sharing riser systems out in the market where 100% of the load path is taken through the main tube only. The reason why you may have a non-load sharing riser system is it creates less complex loading for the aux lines itself, and you just take the tension through the main tube of that riser. The reason why we wanted to highlight this is once you start dealing with an IRJ, if you look at the figure to the right, the lower standard riser joint shows how the tension load path is split between 70% to the main tube and 15% to each LOX line. Now, when we have to adapt the aux lines to deal with a offset difference between the IRJ and the marine drilling riser, you'll see that the lines have to be bent outwards. And as you bend these lines outwards, you're typically not going to want to share load with those auxiliary lines, because anytime you put a bend into place in the aux line and you put them under tension, the bend is going to want to straighten out. And we have seen instances where people have tried to take load sharing through bent aux lines in the past, and they met with challenges with that. So this brings up a consideration for your crossover adapter load rating, is that if you want to maintain the full load rating of your IRJ as compared to your existing marine riser, and you have a load sharing riser system, you may have to have a thicker main tube for the crossover adapter as well as the IRJ, and there may be impacts to the OEM riser connector related to the wall thickness of the weld prep. Your main tube here, shown in gray, which is where my cursor is at, may have to be thicker, but depending on how your crossover adapter is designed, a lot of cases, what we've seen to date is that the drilling contractor will provide a donor joint, whether it be a pup joint or a full-size riser joint, and you would cut that joint in half, and you would cut off the existing marine riser flanges and use the aux line pin and box connections to allow you to weld it to the riser crossover adapters. Now, your weld prep for that specific riser flange may be fixed by the riser OEM. Some OEM flanges allow you to simply trim the weld neck flange on the OEM riser to get a little bit more wall thickness, to get a higher tension capacity. But in some cases, there may not be enough material left on the OEM riser flange for you to allow to trim back the weld prep to get to a thicker wall. So what that may require you to do is get in touch with the riser OEM to see if you can procure a flange that is specifically designed to take to transition from a load sharing to a non-load sharing riser, and they would build that additional weld prep into that flange. And the reason why we bring that up is that could lead to a fairly long lead time. The next aspect that we get a lot of questions on are related to, why can't we have a standard riser crossover joint for different riser systems? And the reason for that is really highlighted in the pictures we have on the slide here. The lower left-hand figure that we have here is a MPD service provider specific flange that has 5 auxiliary lines, and they can be spaced equally around the riser flange in 60-degree clocking increments. And then for this specific installation, we had a look at going with a MH Worth clip style riser connector that had 4 aux lines, with those lines being run 180 degrees on opposite sides of the riser, run in parallel. So you can see here, the crossover adapters have to deal with different clocking positions. The offsets from center line relative to the bolt circle were different, and the quantity of aux lines was different. So even within common OEM riser flanges, if you look at the figures to the right, for a Load King 3.5 riser system, the way we've set these figures up here is that for all these riser flanges, the choke and kill lines are in red, and the red dots are oriented north and south. And that gives you an idea of where placement of the riser boost line would be, the riser hydraulic lines would be, as well as any additional aux lines you may have. And even within a similar OEM of a 3.5 Load King riser system, you could have 2 hydraulic lines, you could have a single hydraulic line, and you could have a boost line that's placed in either a 60-degree clocking position or a 120-degree clocking position. So this can really create a lot of challenges in trying to come up with a standardized riser connector, even across a common OEM for a standard marine drilling riser system. There are also rigs out there that have up to 6 aux lines, to where they may have a glycol injection line. The reason why we wanted to highlight that is in today's market, majority of the MPD riser system IRJs that are out there from the various service providers are most commonly set up to handle 5 auxiliary lines, being your 2 choke and kill, your 2 hydraulic, and up to 1 boost line. So if you have a rig that potentially has that glycol line, you'd want to get conversations going with the MPD service provider fairly early on. That way you can identify the need of any changes you need to make either to the riser system, determine if that glycol line is needed, or possibly look at seeing if it is feasible to integrate that 6 aux line through the IRJ. Now, going back to what we talked about here and looking at different clocking positions, this was the specific set of crossovers we developed to allow us to interface from that MPD service provider's flange over to a clip riser system. So you could see we have the 4 aux lines running in parallel and that we had to bend lines out of planes to adjust for that orientation. The challenge that creates here is you get mild to severe bends when you're trying to clock between 60 even up to 90 to 100 degrees out of plane with aux lines. And what that does is it creates the perfect conditions for buckling. The way we try to arrest buckling is we can try to minimize the severity of the bends to the greatest degree possible, try to take that over a longer length and make the riser adapters longer themselves. But the challenge there is as you add length to the riser crossover adapters, you're adding weight to them. And you may have to procure additional raw materials in order to get that length. Oftentimes, we're going to increase the wall thickness to try to make those lines stiffer. And oftentimes, you're going to have to increase the wall thickness of the lines anyway, because you're going to be taking such a severe bend that that line will thin out near the bends. The reason why we wanted to highlight that is a lot of the times you'd think you'd be able to reuse the existing aux line material from the provided donor joint. However, because of the wall thinning you get from bending, you're likely going to have to procure thicker aux lines in order for those lines to be bent. The other solution to deal with buckling is to add clamps. The challenge with adding clamps is from a design perspective, that's fairly easy to incorporate into place. But when you start considering the overall cost and lead time of the project, procuring additional custom forgings, additional clamp rings, just can add cost and lead time to the crossovers. Another challenge that you can see in dealing with the aux lines is oftentimes you could get to a condition where you may have different internal diameters between the existing riser connector you're interfacing with and the MPD service provider's auxiliary lines. In this example here, you could see that the hydraulic line down here had a smaller ID, and we're using this as an example, but for one specific case, we had to adapt from a 2-inch ID over to closer to a 4-inch ID on the hydraulic line. And when you applied an internal pressure of 5,000 psi, what that did is it created a load imbalance due to the line size change and the piston area inside the aux lines. So that's going to increase the compressive and torsional loads on those lines. And to some point, you have to be able to restrain that. The reason why we wanted to highlight this, and it can become quite challenging for non-load sharing riser systems, is due to the fact that the riser connector itself isn't designed to take any of the load from the aux lines themselves. So if you're dealing with a non-load sharing riser system, the way to restrain that next axial load is to put that load into a clamp. You wouldn't want to put that load into the OEM riser connector, because what that may do is take it out of its API 16F or ABS and DNV certification rating. And any additional load you put into the riser connector may require more detailed analysis, or may require you to beef up to the riser connector and speak to the riser OEM. So that's just something to be aware of, that if you're looking at a non-load sharing riser system, they can be more challenging to manage the aux line bends and pressure load imbalances. There are design features that you can incorporate to manage those, but it may increase your overall lead time of those riser connectors. And the reason why we wanted to highlight crossover adapter design and delivery timeframes is that the crossover adapters themselves are usually the last items to get ordered over the course of your MPD system integration into the rig. Typically, the design and delivery is on critical path. They're usually not thought of very early on when the rig survey is performed to look at start incorporating the MPD IRJ as well as the rest of the MPD equipment. And what we've seen to date is your design and delivery schedule can range from about 12 to 20 weeks with a 16-week delivery on average. Flanged riser crossovers are typically load sharing and they have less design complexity. When you have a load sharing riser connector, you may have a delivery time of 10 weeks to 12 weeks, depending on if you've looked at that riser system in the past. So from our experience looking at the crossovers that we talked about on the previous slide, the very first set of crossovers that were designed and developed by us for a non-load sharing riser system had an overall total fabrication time turnkey of about 21 weeks. It took 11 weeks to complete design with some overlap in fabrication of 14 weeks. as the designs mature and you get more tools in your kit and you start working with more types of riser connectors, you have more kit in your tools to be able to more rapidly complete your design. And you'd have fabrication drawings that are going to be fairly more complete that don't require as many updates. And that can allow us to get a lead time down to, say, 10 weeks for the BHP Invictus MPD riser crossover adapter. That was a Load King riser connector design. It was load sharing, so we didn't have to look at incorporating any clamps. And for that specific riser connector, the offsets and the line sizes were fairly common between that flange and the OEM riser connector and the MPD service provider. So that allowed us to get a slightly better delivery time. But really, from a comfortable planning perspective, if you're looking at schedule for your project, is 16 to 20 weeks really should be considered if you want to have a realistic schedule in order to get your crossovers delivered. And the reason why this is important is you really aren't able to start MPD operations until the crossover adapters are designed. So while they're usually have been an afterthought, we wanted to bring them to the forefront of the project, because the earlier you can start considering designing your crossover adapters, that can really help with the overall execution integration of the MPD IRJ into your marine riser. So we'll continue forward here, and the next half of the presentation is vessel to MPD IRJ interfaces. So we're going to be moving away from the crossovers into other areas that we commonly work in, and those are going to be related to MPD mud return flexible jumper hose assessments. What you can see here is this is an MPD IRJ that has its MPD flexibles installed in the moon pool just below the work platform, about to be splashed subsea. The reason why we perform those MPD hose studies is we want to gain an understanding of what environmental conditions these flexible hoses can operate in. Very early on in MPD operations, and even with rigs, choke and kill, mud boost, and hydraulic lines, there aren't really many analyses out there that tell you what conditions you can safely operate the hoses in to make sure you don't violate the hose minimum bend radius, to make sure you don't have clashing with the hoses and adjacent structures or the hoses themselves. We want to make sure that any hose design limits related to tension capacity and hose twist aren't violated. And we also want to gain an understanding of how much weather veining can the rig tolerate with respect to weather veining due to weather heading between the vessel and the marine riser system. So these studies can be either performed to establish hose hang-off locations that give you an acceptable operability window to be able to perform MPD operations for the hoses, or we can at least try to optimize and look at alternate hose hang-off locations that may give you a more wider range of operability conditions you can cover. These hose studies are required for ABS and DNV certification. So if you are looking at a specific drill rig that has ABS CDS or DNV OS E101 ratings, and you would like to keep and maintain that certification from that particular authority, they do expect the hose analysis to be performed. And the hose studies themselves typically don't have that long of a lead time. On average, once the input data is received, they can take about 2 to 3 weeks to complete. So there's a fairly rapid turnaround on completing these studies. So as I mentioned on the previous slide, we wanted to highlight how we at 2H came up with operability envelopes in order to graphically represent what conditions you can safely operate these hoses in. What we do is we create separate operabilities for each MPD jumper that's installed. Typically, that is at least 2 6-inch MPD mud return lines. You may have a bleed line for servicing your RCD, or you may have a lubricator line for servicing the RCD as well. So in the slot on the left-hand side of the screen, you have the operability envelope. And what you have on the y-axis of the plot is a current speed that increases from 0 to 4 knots. And in the x-axis, you have significant wave heights increasing from 0 to 20 knots. So if you're looking at operating in a 10-foot significant wave height and you have a current that the rig's exposed to of 2 knots, that would put you in this green window here. And what that green window is significant of is that the vessel can weather vane up to plus or minus 180 degrees while maintaining within its hose design limits, being minimum bend radius, allowable twist in the hoses, and its allowable clashing energies. Now, if you were to some reason get into a higher current, say you were operating in the Gulf of Mexico and you were observing 3-knot loop currents, what that would do is it would start to limit the allowable weather vane heading changes that the rig can withstand. So at this point, you'd only be able to weather vane within plus or minus 105 degrees. What these hose studies assess and the operability envelopes encompass is making sure we check the minimum bend radius. Minimum bend radius is typically the driver that limits your operability envelope. So your most common locations of MBR violations occur in the sag bend or belly region of the hoses, which are circled in red here, and in high sea states where you either have high currents up to 3 knots or you start to get to waves that are above 12 to 15 feet or greater, you can start to get hose MBR violations where they hang off at the vessel. You just have so much wave energy and so much current pushing against the hoses that they're going to want to develop a kink point between the hose and the rigid hard piping they're attached to on the rig itself. You also have what we see as clashing. Anytime you have the jumpers placed very close together, you can get clashing in the sag bend region or in the midspan of the hoses, where the hoses will clash with themselves. That typically isn't that big of a concern, but some installations require the installation of 2 flexible jumpers to make up a complete length of, say, 220 feet. You'd have a 210-foot section of hose to make up that total 220-foot length. And what those intermediate connections do is can clash with one another as you move about. That maximum clashing energy can also occur between the hose and the IRJ itself. So what our key findings are to date is when we start looking at the hose hang-off locations, what our key findings are is to date the most significant impact we see on the performance of the hose is the placement of the hoses in the moon pool with respect to the marine riser and the IRJ itself. If the hang-offs are placed too close to the riser or too close to each other, you're often most likely to see MBR violations, which can limit the allowable weather vaning. And in the figure in the upper right-hand corner of your screen, you're going to have MPD jumper return line B, which is also in red. We wanted to highlight this as an example of what we've seen before. Anytime the rig is going to want to weather vane, the hose is going to want to wrap around the riser. So as the vessel would turn clockwise or counterclockwise, that hose wraps around the vessel. In most cases, the outer diameter of the riser would have a smaller radius than the minimum bend radius of the hose. So if you start to look at very large weather vane heading changes past 90 to 105 degrees, the hose is going to want to wrap around the riser, and at that point you've already created a point where the hose is going to want to conform and mold to the outer diameter of the riser, and that may be already below the minimum bend radius of the hose. So in order to optimize your performance, you would want to look at placement of the hoses to try to give more clearance with the hose and the IRJ itself to prevent it from wanting to wrap around the riser to the greatest extent possible, to improve your weather vane heading changes. And then if the hoses are placed too close together, in this case, you could see that if current was pushing against the hose, you could have deflection of the forward jumper into the aft jumper. And as you get the rig heaving or responding to wave heights, the hoses are going to want to clash with one another. In this example here, this is going along with what we looked at in the previous slide. And when we worked with this particular drilling contractor to give them the greatest operability window they could have, we looked at alternate locations for that red jumper, which originally was on the starboard side, just forward of the blue flexible jumper. What we wanted to do here was we looked at multiple iterations to try to improve the operability performance of the hose. But ultimately, what we had to do for this specific installation was move the red jumper to the port side of the moon pool to give us the greatest operability envelope possible. And what that did is it reduced the likelihood where the hose would want to wrap around the riser, and it also reduced contact between the hose and the riser as well as the two hoses, reducing the likelihood of abrasion. And what this gives you an idea here is how the operability envelope changed as a function of placement of that jumper B to the port side of the moon pool. And what that did here is you can see it allowed us to get almost all the way up to operating in a 4-knot current. It has significant impact on increasing your allowable weather vane heading changes for a wider range of wave heights and currents, with going all the way up to the plus or minus 180-degree weather vane heading change, and just gave you general better performance of the hoses for a number of different environmental conditions. The other really key factor that we wanted to highlight that we see today is that hose design stiffness really has the most significant impact on hose performance. The way these hoses are constructed, they're typically bonded flexible jumpers, and as pressure is applied to the ID, the hose gets stiffer. And as the hose gets stiffer, it's going to want to deflect less as current and wave loads impact them, or from dynamic motions of the vessel. So the hose stiffness, you could see here, the left operability plot is what the operability envelope is when the hoses are just seawater filled at zero pressure. And you can see here, the rig really couldn't weather vane much past plus or minus 45 degrees for majority of the operability window. But when that design pressure was applied to the hose up to 2,000 to 3,000 psi, the operability envelope got quite a bit larger. The reason why we want to highlight this, in this case specifically, the hose hangoffs weren't necessarily put in the most optimal locations for this installation, is this really gives us a good drastic comparison to show that how hose performance can be affected as a function of pressure. Not every installation is going to have this drastic difference between zero pressure and design pressure. But the reason why we wanted to highlight this is when the MPD IRJ is installed, you may not always be drilling with MPD. So when the hoses are unpressurized, you still have to make sure the MBR isn't violated and you don't violate the design constraints of the hose, because these hoses are quite costly to replace if they were to be damaged. So if you look at an MPD flexible jumper study, make sure that you're always getting the zero pressure case considered, and that would ultimately be what drives the operability window for the rig. So damage to the jumpers is a real concern, and we've actually seen a fairly good correlation between what our analysis models are showing and where we'd expect to have abrasion. As you can see here on the right, the MPD hoses actually drape well below the IRJ. And if you have any sharp corners from aux line clamps, any fins, any sharp objects around the riser flange related to the OEM riser connector, as the hoses clash with the riser over time, you can get outer cover abrasion. A long time ago, you used to see 316 external carcass wrapped around the hoses. That's not really incorporated as much anymore, because once that cover is damaged, and it's fairly easy to damage, it's not repairable and can start to turn into a slinky on the OD of the hose. The best way to try to mitigate abrasion would be to either look at putting hose protection devices in place, which are these flying saucers here, and MPD hose protections. You can also look at placing a simple fix would be to place a buoyant joint below the MPD IRJ. And what the buoyant joint would do would prevent the hose necessarily from contacting any sharp objects, aux line clamps, on the riser joint that's immediately below the IRJ. Some rigs actually have riser protection or riser guards that are on slick joints below the IRJ. So there are a couple different tools you can put into play here, but we do see damage to these hoses, and it can be mitigated. Moving on towards other aspects you want to consider, that really when you're looking at performing a rig integration study for the IRJ into the drill rig, is you want to look at what your minimum pass-through IDs are and what the rig's riser handling equipment is rated to. The reason we bring this up is the IRJs can be over 100 feet long and can weigh well over 100,000 foot-pounds, depending on which generation and what service provider you're working with in installation of the IRJ. Your pass-through ID, there are typically two areas you want to focus on. One would be the pass-through ID of the IRJ itself through the rotary and the diverter. Most rigs out there with a 60-inch diverter are going to have a minimum pass-through ID of 59 inches. But there's also rigs that have wireline tension systems that have a tension ring stowed below the diverter housing that may have a pass-through ID that's smaller than the ID of the diverter. So any place that the IRJ is going to want to pass through, you're going to want to have a good solid understanding of what those IDs and what those restrictions are going to be. Another item to consider is that once the IRJ is installed, you're typically going to have some type of an RCD or bearing cartridge that would have to be run on the drill pipe through the diverter, through the flex joint, through any spacer joints, as well as the telescopic joint ID to make sure it can successfully drift the RCD bearing. We've seen examples where one OEM service provider had a 19-inch bearing that needed a 19.1-inch drift ID. Well, the base of the telescopic joint had a 19-inch pass-through ID in the load shoe. And while this may look as a stopping point for the project, oftentimes you can work with the OEM of the telescopic joint to try to make modifications to possibly turn down the ID of the load shoe to accommodate that bearing. It may be limited based on the load shoe and the telescopic joint, or possibly the blat tool. But if you look at it early on and you start discussions with the OEM of the telescopic joint, you may actually be able to machine down that ID. Other areas are related to handling. You want to make sure the rig cranes have sufficient capacity to be able to handle the joint and have adequate reach and capacity to place the IRJ on the catwalk or any areas we're going to be storing the IRJ. Riser gantry cranes that are typically used to handle buoyant joints, they'll typically won't have the length or weight capacity to be able to store the IRJ, so they may rule out the use of the gantry crane. So that's why we wanted to highlight the fact that you do want to have a good study to make sure the rig's cranes are able to pick up the IRJ. The other three areas you're going to want to check from a handling perspective are the catwalk systems. You want to make sure you check the capacity of the skates. When you look at the riser catwalk, the forward skate usually has more capacity than the aft skate. What's good to know here is that if you have a catwalk capacity that might have lower rating than the weight of the IRJ itself, you can typically achieve upgrades fairly easy in order to be able to handle the IRJ, but you'd want to plan for that earlier on versus find that out later on in the project, because there can be a lead time associated with getting those upgrades made. The other thing you're going to want to look at is what is the capacity of the riser tailing arm. You may have to have protection on the IRJ to prevent the tailing arm from damaging any delicate IRJ components, being valve bodies or hydraulic lines. And you also want to make sure that the tailing arm has sufficient capacity to be able to transition the IRJ from horizontal to vertical over well center. And as I mentioned earlier, typically the IRJs are going to weigh a bit more than the rig's standard telescopic joint. And with that in mind, your riser setback area is most likely sized to store your telescopic joint. So in looking at deck storage constraints, you may have to look at placing saddles or cradles along the length of the IRJ to try to distribute that heavy load from a point area to a larger area to manage your deck loading requirements. And that really brings us to the conclusion of the key points we wanted to have in this webinar. So the key items to consider when you're looking at the marine riser to MPD IRJ interface is that the crossover adapter designs can often be complex. They're typically more complex for non-load sharing risers than they are for load sharing risers. Plan on having a lead time of at least 10 weeks. A preferable lead time to plan in the schedule would be about 20 weeks, but start looking at crossover adapter design as early as you possibly can. And as you start looking at performing your rig's integration studies or your rig surveys early on, is have a detailed look at where the hose locations can be placed. If you can place the hoses further away from the riser center line, either forward or aft, that's going to give you a better performance window for the hoses. And these rig-specific hose studies are required for ABS and DNCV certification for these systems. So if you can perform these studies early on, it's going to get them quicker to the third-party certification authorities so they can review and approve the study. And it's really going to give you a better idea of where all your interfaces are between the hose to try to increase your operability envelope to make sure you're not over-limited when the hoses don't have any pressure in them. And if you can plan early on for the handling equipment limitations that require review, you may be able to work with OEM providers to get upgrades for that equipment so you can have seamless integration and cooperation between all parties very early on in the project, and that would hopefully allow you to have a more speedy and efficient installation. So with that, we'll turn the floor over to questions.
Thank you so much, Sean. That was great. So I'll just jump in with our first question. It says, can crossover adapter designs be standardized?
That's one of the questions we get quite often is, can we standardize a riser connector? And there are ways that we can standardize crossover adapters, but typically that would be looking at working with a drilling contractor, and say you'd be looking to have 4 rigs that all have common riser systems. So let's, for this example, say you have 4 rigs with an NOV FTH riser system, and they all have common connectors across those 4. We could standardize a crossover adapter design to cover integration of 4 sets of crossover adapters for those 4 rigs. But one of the challenges could be is that FTH riser connector for that drilling contractor may have slightly different requirements with another drilling contractor. So given the variability that we see in the riser connector OEM flanges, even within a common OEM and a common riser system, it's fairly difficult to come up with a common set of riser over crossover adapters that would easily let you buy a standardized kit to plug in the MPD riser system into the string.
Okay, great. Next question. Sorry. Are there certain marine riser systems that are more challenging to design MPD crossovers for?
Yeah, your most challenging MPD riser systems to design crossovers for, which at first when we looked at them was counterintuitive. You would think that going with a non-load sharing riser system would give you the easiest crossover adapters to design because the IRJ itself is going to be a non-load sharing design. Didn't turn out to be the case. And the reason for that is when you deal with the auxiliary lines being bent, and when you start looking at pressure load imbalances, non-load sharing riser systems typically require more clamps to be able to manage the load imbalances and the buckling loads that you get put into into the aux lines themselves. So they're typically a touch more complex to design and take just a little bit more, a week or 2 more to get those design finalized in order to get a successful design for API codes.
Okay, great. Next question is hose swivels can attenuate weather vaning restrictions. Do you have any comments on, I guess, using dynamic swivels instead?
Yeah, typically our MPD hose studies, we're going to look at placement of the hoses. And one of the things we recommend early on is to look at placing hoses largely between the connection from the flexible jumper, between the jumper and the gooseneck connection on the flow spool itself. Having the dynamic swivels really helps reduce the torsional loading you get on the hoses. That way you can take a larger range of weather vane heading changes, and it's also better for loading on the hose long term and can help improve MBR performance even when you're just looking at operating in higher currents, maybe without weather vane heading. So the studies we've seen to date and have run to date definitely show that incorporating swivels is beneficial to the hoses and the operability envelope.
Okay, perfect. Thank you. Next question. Which operating condition is the most limiting to MPD flexible jumper operability?
Yeah, the most limiting condition there goes back to the slide where we had the comparison of looking at the hose with and without pressure. And when the hose doesn't have pressure in it, it's going to want to deflect more. And that condition really drives the operability envelope. And we like to highlight that from the fact of if the rig is still connected to the well in a high C state, you may not be performing MPD operations. You may just be at a temporarily halt in drilling operations while you wait for that weather to pass. And while you're waiting potentially for that weather to pass, those hoses are still subsea and exposed to those dynamic environments, and they're more susceptible to damage when you're operating in higher environmental conditions. So when you look at an MPD flexible jumper hose study, you always want to make sure you look at the minimum stiffness that correlates to having no pressure in the hose. It really isn't a function of mud weight, but having no pressure in the hose is what drives operability performance.
Okay, great. I think we have time for one more. Okay, what are the key vessels to MPD IRJ integration challenges to look at early on in the project?
I'd say looking at your handling constraints of your equipment. A lot of the times, depending on the IRJ you're working with, They can weigh well over 100,000 pounds, and some rigs have a catwalk capacity rating of 88,000 pounds. 88,000 pounds tends to be that magic number in dealing with catwalk systems where uh, the rig's cranes are usually going to have more capacity than the catwalk. So usually where we see the limiting capacity is on the catwalk machine. So looking to see if any upgrades are required on the catwalk machine is really the key area to focus on when you're doing the rig study early on up front.
Okay, great. Well, I think that is all the time we have for today. So I just want to say thank you, Sean, for all the information on the topic. And if we didn't get to your question, or if you think of further questions, you can definitely contact Sean using the details provided here. And thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening at the end of each month. You can check out the 2H website and LinkedIn for more details and to sign up. Again, please look out for the recording of this webinar in your email in the next 24 hours, and we hope that you all enjoy the rest of your day. And thank you so much.
Yes, thank you, everybody. Have a great day.